Okay, good morning everyone. So let's continue on with chapter 18. So let me recap from this point, which was, this point actually, which was this was talking about the states of a gas. So this is actually a pretty central concept in terms of the stuff that we'll be doing for this in the next chapter. So I just want to make sure that you get this point. But if you have a gas, then you can basically describe its state just using these four parameters of pressure, volume, temperature, and the number of moles. And basically all the other kind of degrees of freedom, like, you've got these molecules going around at different velocities. Somehow all these don't really matter, and you can more or less think of just these unique, this set of parameters, P, V, T, and N, as just describing the state of the gas. And if they have the same pressure, volume, temperature, and number of moles, then for for all intents and purposes, it's the same state, right? So that's kind of a central concept in this whole thing. It's not really an obvious statement. You might think, well, what about some other parameters, like, I don't know, some other variable that describes these gases, and for some reason it doesn't really matter, and these four variables are the main parameters. Okay, so basically what we're going to be doing is playing with these kind of four different parameters and understanding the relationship between those and other quantities like work and heat, right? So firstly, the work done is, what we worked out here is that, well, work is like force times distance. That's what we already knew from the previous mechanics chapters. But we can recast it in terms of these gases, and because we're going to be talking about pressure and volume and stuff like that, it's, instead of force times distance, it's much easier to look at this in terms of pressure and volume. So work in this context is like pressure times the change in volume. And if the pressure is changing, then you need to integrate it. That's a lot like how if the force is changing, you need to integrate it instead of just multiplying it. But if it's a constant pressure, then it's just P times delta V. And this was just talking about kind of how to think of this in terms of forces, but right. And then another important thing is these pressure volume diagrams. So the key point of these things, again, comes down to this fact that the state of a gas can be described by just these four variables of pressure, volume, number of moles, and temperature. And later on, when we'll see that PV equals nRT. Probably some of you might have seen this equation already. So actually, these four variables aren't even independent. So in fact, one of these, and we're going to say that it's going to be temperature, one of these is more or less dependent on the other thing. So if you know the pressure and you know the volume and you know the number of moles, actually then you know the temperature. So you don't really, one of them is not really a degree of freedom. So basically then we're down to 3 degrees of freedom, P, V, and N. And then often we're just thinking about systems with a constant number of moles. So, if you've got a gas in a jar, the number of moles is not going to change unless the thing's leaking. But basically, in a lot of cases, the number of moles is fixed. So that actually eliminates even one more because it's basically constant. So it's just P and V. So P and V just tells you basically the state of the gas, right? So basically, this PV diagram is not just simply just the plot of this pressure and volume, but it's really a kind of a map of all the states that you have in the system. So every point in this state, in this diagram here, is a kind of a different state of the gas. And so it's not just some parameters of pressure and volume. You should view it as a map of all the possible states that the gas can be in. And then, so if you have two values of P and V going from A to B, then this is really like saying, okay, I'm going to start in state A, I'm going to go to state B, and I'm going to, I'm going to go from A to B in some kind of trajectory, which is mapped out in this graph. Not only is it a map of all the states, it can also tell you information, because we just said that work is integral of P times dV. That's why we normally draw P on the vertical axis, V on the horizontal axis. Then the area under the graph here is the work, right? So we can actually evaluate certain things. So that's why this PV diagram is a super important concept in the relation, in the context of this thermodynamics. So we looked at a couple of examples. So constant temperature, right, so the constant temperature, maybe I didn't mention this last time, but constant temperature looks like this, but basically, again, because, well, we haven't really done it yet, but let's sort of preempt things, right?
Is
so,
it presenting the
yeah, it's fine. Yeah, great, thanks. So we haven't done this exactly yet, but maybe some of you have already seen it. So constant temperature basically means, and again, we're just considering constant number of moles. So all these things are basically constant on the right-hand side here. So if we just rearrange this equation for P, so this is, y-axis is P, x-axis is V, right? So basically then it's like a graph that looks like P equals something over V, a constant over V. So this is why these constant temperature processes kind of look like this, because 1 over x looks like this. Right? So that's why this constant temperature case is a graph that tends to look, it's like a curved graph that looks something like this. In this case, if you expand the volume, then you're going to have some positive amount of work. So in this case, you might reduce the mass here. So we can also think of a constant pressure process. In that case, we're going straight across here in the PV diagram, and then perhaps down like this if we're going to end up at the same point. In this case, the work is actually going to be bigger than whatever we did in a constant temperature process. Constant volume in this case, if we go down in pressure first and then across in volume, basically do those two steps kind of in reverse in part B, then we'll have even smaller amount of work. And if we start and end at the same point in the PV diagram, then, as I said, each point of this represents a particular state. So that means that we're going to end up at the same state as the beginning, right? If we go around in a circle. And because if we go in the opposite direction here, this will be negative work, and going this positive direction, by positive I mean this is expansion and this is contraction. Right? So when you expand, you always do positive work. And then so basically the net work that would be done would be the area enclosed in this cycle. Right, and this is basically where we left off. So let's try this question. So PV diagram here shows 6 curved paths that can be followed by a gas. Which 2 of the curved paths should be part of a closed cycle if the net work by the gas during the cycle is to be maximum positive value? takers. Well, I've given you multiple choice, so let's look at this one. So AF, so if we go around this loop, so A and then F, so this is like the largest possible square. So I've said that the work is the area enclosed in the loop, the area that is enclosed by the loop. So obviously this will be the largest area. What would be the problem with this one? I'm already implying that it's not the right answer. So if we go back, the work in a cycle, well, work is area under the graph, right? So it's like this area. And if we expand, then this is the V initial, V final. And I said work is pressure times V, and then what you'll do is you do some kind of integral like this, right? And pressure is always positive, okay? So we don't have to worry about pressure being negative. But then if the volume, so if the volume, this VI is less than VF, then is this positive or negative? Okay, so we don't even have to know any physics here, right? Okay, so we've got some graph telling it's positive here, right? And if we integrate with this limit being larger than this limit, is positive or negative? Positive, yes, because, well, it's just a graph, it's positive. P itself is positive, and this integration is going this way, right? But if it's the other way around, if we have this VF, this limit is the lower limit, right? And this is the upper limit, and basically we're integrating this way, and is the work positive or negative? Right, negative, right? So basically, if we're going this way, it's positive, and if we're going this way, it's negative, right? Okay, now if we're looking at a cycle, okay, so we can break it into two parts, right? So if we have some cycle, this is P and V, then for the first leg, this is the work, yeah? This is step one, right? And then in the second step, if I just draw the same diagram, it's supposed to be the same. So this is for step one. And then for step two, it's going, this is the work, right? Two, yes? So this is negative here, right? So it's going to be W1 minus W2, which is the area here, yes? Okay, so given that, so if I've got a cycle like this, going A this way and then F this way, is the work done in that cycle is going to be positive or negative? Yeah, it's going to be negative because in this first leg, this is going to be a large negative number, right? And in the second leg, it's going to be a small positive number. So this is a cycle, and the work done is it's the area enclosed by the loop, but it's a negative number because it's sort of going the wrong way. Okay, so that kind of tells you that if you wanted to do positive work, it needs to be going clockwise, not anti-clockwise, right? All right, so then basically the question is like, which is the largest clockwise loop you can make? Yeah, C&E, yeah. So that's the largest one that's actually in the positive direction, and this is the smallest one that's in the negative direction. So yeah, C&E. Okay, so this brings us to the first law of thermodynamics. So obviously this is, you know, one of the central concepts of this chapter. Okay, so basically the idea is like this. So we've got our PV diagram like this, right? And then I've said that these P, V, and T, these tell you something about the state of the gas. So that combination gives you some state, unique state of the gas, right? And then, in fact, the temperature is often, you know, only just dependent upon the pressure and the volume, like if you've got a fixed number of moles. Okay, now, First Law of Thermodynamics says something like this. So let's consider two points, two states of this gas, right? So the first one is, say, P, PI, VI, TI, and the second one is PF, VF, TF. Okay, and then and actually, maybe I shouldn't have even written the temperature. So you can just think of it like PI, VI, and then PF, VF. Just don't worry too much about the temperature. This is the common case that we're going to be looking at. Okay, now look at like three different possible paths to get from the first state to the second state, right? So we might go like along some path like this A, or like B, or C, okay? Now, all these three paths will have different values of the work, obviously, right? So, like in path A, the work is the area under the graph here, right? So that's that area there. For B, there's an extra bit here, which is because, you know, it's a large area, and then C will have the largest area under the graph. Yeah. So they all have different values of the work. Yeah. They will also, in general, all have different values of the heat, right? So the heat that goes into it, going from these 2 points, will all be, in general, different. Okay. So in general, you know, this heat and the work, they're path-dependent processes. Yeah. But so the magic here is that if you actually do heat minus work, then it will be the same for all these different paths. And that's a little bit of a non-trivial thing because, as I said, you know, we have two things which are like heat and work, which will, in general, depend upon the path that you take. So if you're starting in this state and going from this state, you know, the amount of work that you do, the amount of work that the gas does is going to be different for each path. That's obvious from this graph. The heat will also be different. It's not, you can't really see it from this graph, but in general it will be different. But if you do this quantity Q minus W, then they will all be the same regardless of the path. So there's something kind of magical happening here because you know, we have two quantities which both depend upon what path that you're taking. So, you know, here you're changing the pressure or changing the volume more quickly first, right? So here you're expanding it so kind of more quickly, and then you're dropping the pressure here. You're dropping the pressure first, and then expanding volume later. So all these things will, in general, be different numbers. But then if you do Q minus W, you just all get the same number for all these things. So this is a pretty kind of amazing fact. Well, it's already amazing that you can describe the gas just by a couple of these parameters, and somehow the rest of the things don't really matter. That's kind of already amazing. But then it's kind of doubly amazing that there's a quantity that doesn't really depend on the path. It's kind of purely apparently dependent on the state, right? So there's something intrinsic that characterizes the state here, such that it's only dependent upon basically the initial and endpoints. So this special quantity, we call it the internal energy. For reasons which I'll say in the next slide. And so the first law is basically stated as the change in this internal energy. Well, this is just a definition, really. Q minus W, more or less. Is it a definition? Yeah, but so okay. Well, it depends on whether which way you think about it. But later on, we'll interpret this quantity as an internal energy, and so, well, if you take the point of view that it's that this internal energy is something which we're just introducing right now, then it's kind of a definition. But the main point here is that it's there's something intrinsic to the gas which you can evaluate using this expression Q minus W. We can also write it in a differential form. This just means, like, if you did a tiny change of the state of the gas. So say here you're changing it from PV to PIVI to PFTF. These might be quite different values, but let's say you bring those together to two values so that they're very, very similar to each other, they differ just by an infinitesimal amount. In that case, of course, the work will be also infinitesimal. The heat will also be infinitesimal because these are just about the same. And then we'll write the internal energy change also as kind of dE, just to reflect that this will be some small amount. And we tend to use this if you're going along some path which is some more complex trajectory. But I think for most of the time you can just use this first expression. Okay, so the bullet point here is the internal energy of a system tends to increase if the energy is added as heat, and tends to decrease if the energy is lost by the system. So, perhaps maybe we can come back to whatever that was talking about. But let's talk about why this might be. Okay, so we might. Basically, the way to think about it, this is a conservation of energy statement. So the way to think about it is that we've said that this PVT, that assigns some unique, numbers which specify the state of the system, right? And the way to think about it is that, well, each one of those configurations has some unique energy. Okay, so maybe microscopic, when we will do this microscopically, is that, so if you've got a bunch of atoms in a box, they're all flying around, and this will have some pressure, volume, temperature, well, also a number of moles. And these atoms will possess some total amount of energy. And what we're going to see is that actually the total amount of energy is essentially just the sum of all the kinetic energies of all these atoms. Okay, so basically this PV and T and N, for each configuration of that, there'll be some value of energy, and that energy is basically only dependent upon these parameters, so PV, T and N. So there'll be just some energy for that particular configuration. And what's happening here is that as you go from this initial configuration to the final configuration, this will have some difference in internal energy. So there'll be some internal energy of the gas here, be some internal energy of the gas here. And that change in internal energy, in this case, can only happen kind of in two ways. So the gas can do some work. For example, if it expands and then this piston goes up, then the volume is expanded, and as we've been saying, the work is P dV integral. So this means that, and for example here, like if you look at this mass, it gets lifted up, right? So the gas has actually done some work for you. And so that is actually energy that has been expended by the gas. And that energy has to come from somewhere. You don't just get anything, just don't get that for free. So if the gas does some work for you, then the gas will lose energy because it's just done some heavy lifting here and expended some energy to lift this mass from this lower point to this high point. So this is why it's got a negative sign. So if it does the work, if the gas does some work, then it will lose energy itself. So that's why the change in internal energy associated with the work will be negative W. In the meantime, let's say you also heat the gas, right? Now, heating the gas means that actually you're giving the gas energy. So if you're putting some flame under it and then you're heating up the gas, you're actually increasing the energy of the gas. So because the way we define it, if we apply some heat to it, that's a positive quantity, and so the internal energy of that will actually go up. So Q is the heat that's being put into the system. W is the work done by the gas, so that's why it's got a negative sign. Okay. So just to come back to this point, so the internal energy of the system tends to increase if the energy is added as heat. Yes, because if you're adding heat to it, you're basically giving the system energy, so the internal energy will go up. And it tends to decrease if the energy is lost to work, because work is actually done by the gas, and so it's losing energy. Okay. Right, so, okay, well, firstly, is that clear? Because this is a pretty central concept of the chapter, so I want to make sure that everybody gets that. All right, so let's do this question then. So the figure here shows 4 paths taken on a PV diagram, along which a gas can be taken from state I to state F, okay, so from here to here. Rank the paths according to A, change in internal energy of the gas. So 1, 2, 3, 4. Which has the largest internal energy change? Yes, it's the same. Right, because the internal energy is only dependent upon, it's not a path-dependent process. So that means it's only dependent upon the initial and final endpoints. And so the paths will be, internal energy changes will be the same for each of the paths. Okay, the work done by the gas, which is the largest one. Alright, 4. Yes, 4, 3, 2, 1. That's right. Because work is the area under the graph, and that's got the largest area of the graph. All these go in the positive direction. So these 4 is the largest. Yeah, 3, 2, 1. Yeah. And then the magnitude of the energy transferred as heat between the gas and its environment. We're doing C at the moment. So it's probably either 1, 2, 3, 4 or 4, 3, 2, 1, right? So which one? Who thinks it's 1, 2, 3, 4? Okay. Who thinks it's 4, 3, 2, 1? Who thinks nothing? All the same. Just okay. So first law says delta E is Q minus W, right? And we're talking about the heat, so let's just rearrange this for Q. So delta E, Q is going to be delta E plus W. And so we said that the work, for 4 was the largest, yes? And these are all the same, yeah? So that basically, so basically it's like, so Q4, then these delta E's are all the same, right? So Q4, well, W4 is the largest, and W1 is the smallest, then Q4 must be the largest, Q1 must be the smallest. This is why it's helpful to actually sometimes actually just write down the equation. I mean, you might think that, oh yeah, because the work in the cube, got a different minus sign, so it must be the opposite, right? But actually, if you think about it or write down an equation, then you can see that it has to be this way around. Another way, maybe a more physical way to rationalize it is that, so, the initial and final points have the same, all the initial points and all the final points for all these four processes, they're physically the same, right? Now, if 4 is expending a lot of work in order to get from initial to final, yet the change in its energy has to be the same, then something has to sort of compensate for that, right? So basically, in taking this route 4, the gases expended a lot of work, right? It's like, you go from, this point to another point, but then you run up a huge mountain and expend a lot of energy, and then go to the final point. 4 is like a really tough route for this gas to go. 1 is a relatively easy route for the gas to go in terms of the work that it's done, right? But yet it ends up with the same internal energy at the end, right? So this must mean something must compensate for that. So basically, in order to get to this same point, even though it's expended a lot of work, there must be a lot of heat that's been added to it to make up for the fact that it's expended a lot of work, right? Does that make sense? Okay. All right. So let's look at some special cases of the first law of thermodynamics. So we've basically got these three variables: delta E, Q, and W, and setting some of these values to 0 gives some special names to these particular processes. So basically, we're going to talk about 4 different special cases, and these are special cases where basically we set one of these variables to 0, and it's it's got a special, it's a more specific case, but it's something that we'll look at. And then the last one is setting everything to 0. Okay. Now, of course, you can't really set 2 of them to 0 because then the third one is going to be 0, right? So that's why you either set 1 to 0 or 3 to 0. So there's nothing like you set 2 to 0. Okay, so the first one is setting Q to 0. So this is called the adiabatic process. And in an adiabatic process, basically no heat goes in or out of the system. Okay, so maybe a nice way to visualize it is that you've got some, say, piston here, which is sort of our prototype system for this. But then we surround it by cotton wool. So this is supposed to be cotton wool or some kind of insulation. And if you insulate it very well, no heat goes in or out. And so the only change that you can have is, or change in internal energy arises purely from the expansion or contraction process, right? So if you expand or contract the gas, then there will be some work done by the gas, and that will change the internal energy. And in this case, just setting the Q to 0 in the first law, the change in internal energy will be just minus W. Now, somehow in the book it says something about you can slowly remove the lead shot expansion without any heat transfer. I think it doesn't have to be slow. In fact, the common example that people talk about for adiabatic processes is like opening a champagne cork. You might have seen pictures of this. Champagne pops out, some mist-like thing comes out, and in fact, the gas there kind of cools down. And in fact, in that case, that's also said to be an adiabatic process, but that is adiabatic basically because that expansion happens so fast that the heat doesn't have enough time to get into it. So it's clearly not insulated or anything like that, but it just happens so fast that the gas expands really fast, and then the heat just takes a little bit of time for it to get in there. So before that happens, it's basically an adiabatic process. But even though that's also adiabatic process, maybe this is, for me, I think, just clearer case. You just insulate it and then no heat comes in or out. Okay, constant volume, as the name suggests, basically means that the volume doesn't change. And if the volume doesn't change, then thing does no work, right? Because work is P times change in volume. So volume change is 0, work is 0. Okay, if work is 0, then the change in energy is purely due to the heat that enters or exits the system. So for example, if you have some gas, put some ice cubes around it, but then you pin the size of the container, so this mass doesn't matter really, then the pressure will drop, I guess temperature will drop. So so the internal energy of this system will drop, right? Because basically heat is leaving the system. Well, okay, Q will be a negative value in this case. So Q takes a value of a negative number, and hence the internal energy change will be negative. A cyclic process, so we've already basically done this one. In a cyclic process, as we said, the internal energy change is 0 because the state is actually, it returns to the original state, the beginning, and each state has a kind of a unique value of the energy here, and so the change in the internal energy is 0, and if the change in the internal energy is 0, then Q equals W, right? So we worked out that the area enclosed in this loop here is the work, but actually what this now tells us is that it's also equal to the heat that's gone into the system. So we didn't just get the gas to do some work for you for free. In fact, that work came from you actually giving the gas some heat, right? So basically you, altogether in this process overall, you've given that gas some heat. But what it's done is to convert that heat into work, right? And work is something useful to us. Heat is something that's a little bit uncontrollable for us. Light a fire, it's heat everywhere, it's just heating everything up. But I mean, apart from getting cozy and stuff, if you want to do some mechanical work, it's not as controlled. And so this actually gives you a way of converting that heat energy into work, and this is exactly what you want to do in an engine, right? So some process that looks like this might look like this. You first heat up this thing, the thing expands, and then so that's I think we're starting here, right? So constant pressure, we go across like that, then we go down like this at constant volume, and we might cool it down at this point. Then we will contract it by taking these pins out, and then it contracts, and then we fix the volume again, put the pins back in, and then apply some heat, it'll go up, right? So this is actually some kind of engine, actually. So it's a bit of a bizarre engine where you're putting in pins, cooling down, get ice cubes, and heating it up, cooling it down. It's a bit weird, but fundamentally this is actually some kind of engine, right? Because it achieves the purpose of overall you're actually adding more heat than you are than it's leaving. So if you added up the amount of heat that you put in here versus the heat that you're taking out of it, that's actually overall a positive quantity, because eventually this thing is actually doing useful work for you. Finally, this is a bit of a weird one that I don't know when it really comes into play, really, but well, it's in the book, so let's go through it. So free expansion. So this is a case when a gas expands into a vacuum. So in this case, we have a gas, and then suppose there's a vacuum over here, and then there's some valve that you can just quickly turn, and then the gas will rush into the vacuum, right, obviously. Now, this is an example where actually the, oh, and by the way, yes, and it's heavily insulated so that it doesn't have any heat go into the system, okay? So in this case, actually, so the heat is zero by construction. You put insulation all around it so that there's no heat entering the system. But actually the work is also zero in this case. And certainly it's not because the volume is zero, like in the other case. The volume has expanded, right? So, but in this case, it's not that the volume is zero, it's actually the pressure is zero. As in the pressure, well, you know, if you imagine your piston to be sort of here, if you like, and then it's fighting against, well, normally it has to fight against atmospheric pressure to expand, right? But actually, there's no pressure here. So in fact, this is an example where the work done is zero, not because the volume is constant, it's actually because the pressure is zero. And then in that case, the work done is also zero. So Q is zero, work done is zero, so then it must mean that the internal energy change is zero. So kind of, you know, it's not sort of really so obvious, but in this example, when you have this gas that expands into a vacuum, the internal energy of the gas doesn't really change in that process. You know, intuitively, it feels like it should change in energy, but I guess if you work out the fact that, well, there's no heat going into it, and also if it does no work, then I guess the energy of these atoms basically doesn't change. Okay, but so that's an example where the heat, the work, and the internal energy is actually all zero. Yeah, so just to summarize, basically, you know, just from this relation here, we can deduce, so if the heat is zero, adiabatic process, then follows that the internal energy change must be negative of the work. If the work is zero, then internal energy change must be equal to the heat. If it's a cycle, then Q must be equal to W. And if free expansion, then everything is zero. Okay. All right. For one complete cycle, as shown here in the PV diagram, are the internal energy change for the gas and the net energy transferred as heat positive, negative, or zero? So, okay, so is the internal energy of this cycle positive, negative, or zero?
Zero.
Yes, zero, because, well, we've done it many times now. So, in a PV diagram, it goes around in a loop. Each point is a unique state. Each state has a unique energy. If it's the same initial and end points, then the internal energy change is zero. Okay, the net energy transferred as heat, is it positive, negative, or zero? negative, right. So how did you work out it's negative?
Because Q equals delta E minus the down by gas, and then the down by gas is factor.
Right, yes. So exactly, yes. So we've got a cycle. So this one is 0, right? So that's 0. So then Q is equal to W. And then we just have to work out what the work is. And Q is not so obvious from this graph, but work we can work out from this graph, and it's just the area enclosed in the loop. And then we just have to look at, okay, so is this loop going clockwise or anti-clockwise? And because it's going anti-clockwise, that means that the work must be negative, because the work in this first leg will be a larger negative number than the positive number in this backward leg. Yeah. Okay. So the work is negative, and so the heat must be negative. Okay. Well, let me do this example question for you. So this is just to finish off this chapter. So this is a pretty typical kind of question that you might get in an exam. So you should definitely practice these questions with these PV diagrams in it, because this is sort of the classic theme that's in this particular and maybe also the next chapter too. So gas held within a chamber passes through the cycle shown in this figure. Determine the energy transferred by the system as heat during the process CA. So that's that length. And we want to work out what the heat is. If the energy added as heat in AB is 20 joules, no energy is transferred as heat during process BC, it's this one, and the net work done during the cycle is 15 joules. Alright, so what I like to do here is actually just it's a little bit maybe overkill for this particular question, but I think it's not that overkill. So what I like to do is basically do something like this. Draw a table. And then, so what do we got here? So AB, BC, CA. And it's a little bit like these logic puzzles where you kind of work out one thing and then from that you deduce other things. Right. Okay, so let's just fill in this table of like all the information that we have, okay? So, well, firstly, the thing that we want to work out here is the heat during process CA, okay? So this is the thing that we want to work out. So this is our kind of target. We might not fill in the entire table, but it's fine. As long as we get that answer there. Okay, so if energy added as heat QAB is 20 joules, okay? So this one is 20 joules. No energy transferred as heat during process BC, okay? So this one's 0. And the net work done during the cycle is 15. So this one is sort of the total, which is going to be like the sum of all three processes. So clearly in the whole cycle, it just has to be the sum of all these three things, right? And so we're told that the net work done during the cycle is 15. Okay, so that's the information, well, that's at least there plainly in the question. So these three numbers here would add to that, but we don't really know what these ones are. We're not really given a graph of the pressure, exact pressure or volume, so we can't really work these ones out. There's one more piece of information here that we can fill in the table that basically will that we can basically figure out what this one is. Can anybody spot what it is? Yep. That's right, yeah. Okay, so delta E should be 0 because it's a cycle. And that one, right? That delta E should be 0, right? Because, of course, delta E in any of these ones, well, could be something. But then the total, because it's the whole process, it should be equal to 0. Okay, so now that we've got that, what do we do next? Right, yes. So basically each of these rows here, we can use the first law to fill in. But we need two of them in order to fill in the other ones, right? So actually here we don't really know what that is. Here we don't know what that is. Here we don't know. But here we can do that, right? So we know delta is 0, we know work is 15, so that means that basically in this case Q is equal to delta E plus W, so this is 15, okay? All right, and then now we've worked out that that's 15, we know that this total has to be equal to 15, right? So obviously it's minus 5. So, we weren't able to fill in the entire table, but, we didn't really need to for this question. Of course, for the purpose of this question, we could have done it a little bit simpler. We could have said, for cycles, I know for cycles, Q is equal to W, and then so I can just work it out from here. But sometimes, I think it's actually just easier to draw this full table. So whenever you get a question like this, you can just draw this full table, fill in the things that you can, and then you kind of just piece it together from there. You don't have to fill in the whole table. Okay. All right. And so finally, okay, so that wasn't the final thing in this chapter, but I think this one is. It's a little bit of a kind of a loose end here in terms of the topic here, but another, well, I think, right. So I think we learned, in high school or even lower, the way heat transfers is through conduction, convection, and radiation. So this is the last thing that I think we do in this chapter. Now there is a kind of a formula that tells you how much heat is conducted through a solid object. I think the easiest way to think about this is think of it just in the exact same way as electricity. So if you're calculating like the resistance of something, then obviously the fatter the wire, right, the lower the resistance, right? Or the longer the wire, the higher the resistance, right? And heat conduction basically works in exactly the same thing. So basically, say you have some, maybe it's easiest to think of some metallic object first. So have some poker here, and one end's in the fire, and the other end's you're holding it. Obviously, what you don't want is for the poker to transmit that heat too fast to you, because obviously if you just leave it in the fire for a long time, you'll start to feel the heat of the fire coming through it, but then if it's not so long, then it will not heat up so much. So in this example, you don't want this to conduct the heat very quickly, right? Now, to work out like how much heat is actually being transferred, so this is actually expression for the power. So this is like heat per unit time, and as I was saying, it works a lot like how resistance works in a wire, right? So basically, the fatter the object, so in this case the poker stick, metallic stick, the fatter the wire, the more heat that will be transferred. It's a lot like how resistance, or like the more electricity, or the resistance will be lower, and so the current will be larger if you've got a fatter wire. So there will be higher energy transfer if this is a large cross-sectional area. The longer the thing is, actually it's inversely proportional to that, because the longer it is, the less easy for the heat to actually transfer. It's a lot like just like electricity. The longer the wire, the harder it is for the electricity to get through, because the resistance is higher. And then finally, of course, the larger the temperature difference between the two ends, the more heat will be transferred. So, obviously, if you're sticking this in the fire versus just sticking in a coffee cup, the amount of energy that you're going to be receiving on the other end is going to be much less for the coffee cup. So, and there's some proportionality constant which basically tells you how quickly that energy gets transferred to you. So it's units of watts per meters Kelvin, and it's per meter because there is this is cross-sectional area on the top, and then this is length on the bottom. So the area divided by length is units of meters. Okay, there's another kind of classic kind of question in the context of this, and basically it's always this type of question, so I would highly recommend that you do a question that's like this. And basically the question is, so suppose you have a composite slab, right? So say you've got two materials and stick them together. So the classic example of this would be some kind of insulation in your house, right? So this is the outside of your house. It's winter, it's cold outside. This is the inside of your house. It's nice and warm. This might be like some foam, so K2 might be some insulating material. And then K1 might be the wall itself, okay? And then the question that is often, that you often get in this context is like, so if you know what the temperature outside is, and you know what the temperature inside your house is, and you know what the thermal conductivity, let me call this thing, thermal conductivity coefficients. Okay, if you know what those K1s and K2s are, then what is the temperature at that interface? So, if this is like today, it's like 5 degrees, and inside you've got 20 degrees. Obviously, it's going to be something in between. It's going to be like somewhere between 5 and 20 degrees. But what is that temperature just to that interface when between the foam and then your brick wall? So that's the classic question in terms of here. So how do you work that out? Well, basically the observation that you make is that the power that's transmitted, this power is in the heat per unit time, that power is the same through these two materials, right? So any power that goes through material 2 here also goes through material 1, right? And so basically what you can do is you can say, okay, well the power that's gone through material 1 is equal to that. It's given by that formula there. Power that's gone through material 2 is equal to that. And the interface has some temperature X. This is the thing that we're trying to find. So we've got the hot end and we've got the cold end. And because these powers must be equal, this means that now we have an equation for this temperature X, because we didn't know really what the power is, right? The question will probably not tell you what the power is, but because we've got 2 equations, we can just eliminate the power out of here. And from there, we can work out what this temperature is. And then it's just a bit of algebra to work out what that temperature is, which we do that. Okay, so we're going to equate these things. So we're saying P1 is equal to P2. So then K1A T hot minus the unknown temperature Tx L K2 Tx minus Tc. So notice this has to be in between Ts, Tc and Th. So this is why this one's the other way around. Like this. Okay, and then we just have to rearrange this equation for Tx. Okay. So let's first cancel this area. It's the same area because each of these materials have the same cross-sectional area here. And, okay, so just rearrange this. So K1 L2 Th minus Tx equal to K2 L1 Tx minus Tc. Then put the Tx's on the other side. And then put the Tc on this side. So K1 L2 Th plus K2 L1 Tc is equal to K2 L1 Tx plus K1 L2 Tx. And then we can factorize the Tx here. And then so it's K1 L2 Th plus K2 L1 Tc divided by K2 L1 plus K1 L2. Okay, so that should be that thing there, right? Yep. Okay, probably got my variables mixed up. Right, okay, yeah. I think I just defined the variables wrong somehow. Okay, so I'd say maybe it's here. One is T, right, yeah, okay. So, I think I defined 1 and 2 the other way around. Because this one is P1, right? And then so this one should be the Tc and Tx one, right? Because 1 is on the cold side, but yet I've got the Th here. So this is why the So if I just replace 1 and 2, then it should be fine. Okay, so maybe I'll fix that up in the slides. So that's expression for the temperature, and then well, you can substitute this thing back into this formula, and then you can evaluate the value for the power. So this isn't, I would say that this is not, like this formula is not something that I would really remember. I would just kind of work that out on the spot, or you know. So you know, you kind of, I forget if this one was on the formula sheet or not, but you know, from this power relation, I would just kind of work out what this formula here is. Basically, you just need to remember that logic of the power should be the same, and then you evaluate the intermediate temperature. Yeah.
Is Tx an arbitrary point that we choose between these two?
No, it's the temperature at that interface here. Yeah. So the question will be like, what is the temperature at that interface between material 1 and 2? Yeah. All right. Okay. So we'll leave it there. Continue on. Let's show.